So hello everyone, welcome back, right? So we are talking about, I believe, acids and bases, and thus in this context we have discussed kinetics, and we have talked little to no aspects or covered little to no aspects with respect to kinetics. Why is that? Because in acids and bases, or in those systems, I guess, the kinetics is so fast that in general you will almost always end up achieving equilibrium by the time you analyze the system now, right? So we did away with kinetics and we started analyzing equilibrium or looking at the various aspects with respect to equilibrium. So equilibrium, again, what does that give you an idea about? It's the state at which, or the state achieved when the system has gone to the maximum extent or farthest extent possible under the given conditions of temperature and pressure, right? So in that context we have moved forward. I believe we looked at the various examples or importance of acid base systems and pH specifically, why it's a master variable. So think of air or oxygen, right, and it's the source of life now. So similarly pH has its hand in each and every pie with respect to the environmental engineering systems. As we go further down and look at most of the applications, you will see that, I guess. And in that case we want to be able to relate, let's say, which acid is going to be present as the protonated form or deprotonated form and in what fractions, right? Because you want to know, can it be removed by ionization fractions or such, and thus you want to look at, is it charged or uncharged, right? Can it release a proton, or can it actually act as an acid at that particular pH, yes or no? So to be able to cover these aspects or understand these aspects, we looked at the Henderson-Hasselbalch equation, and what did that give us an idea about? It gave us an idea about pH in relation to pKa and the concentrations of the deprotonated form A minus by the protonated form HA. So that's the aspect there, right? And then I believe we moved on to discuss ionization fractions in the last lecture class. So we are done with more or less being able to understand the background with respect to the acids and bases. And one particular aspect that we come across is the acid dissociation constant Ka, right? And in this context, Ka, or the pKa value, which is the negative logarithm of Ka, gives you an idea about the strength of the acid. So what do I mean by that? Let's say pKa of HCl, I think 0 or less than 0. So what does that mean? So at almost all the pH values, because pH 1, 2, HCl is going to dissociate into H plus and Cl minus, or it can actually donate the proton, or it will act as an acid. But for example, if I take acetic acid pKa is 4.76, I guess. So at pK or at pH 3, the acetic acid cannot donate its proton, or only some of it, or a small fraction of it. So thus we call that relatively, I guess, a weaker acid, right? All these terms are relative. So how do you quantify that? You can look at that with respect to the pKa, right? So now what we are going to discuss now, I guess, is, you have multiple systems out there in nature, either in water, air, and so on, let's say. So for example, a particular concentration of a particular acid is introduced into the system. What is my equilibrium going to be with respect to the change in pH or the change in species concentration? Species as in the concentrations of those compounds or compounds present at equilibrium. So this is where the crux of the class lies, right? You want to be able to quantify the changes and what you would expect at equilibrium. So in that case, let's go on, I guess. So now we are going to start looking at developing models, especially when you have multiple reactions, right? And in this context we already discussed the models, and I believe we talked about this model, specifically the component balance. We introduced this concept of the building block called the component in terms of equilibrium, right? So we are not going to go into that in detail again, but we are going to have a problem solving session. So throughout the class we are having some problem solving sessions, but this time we are going to have it in tandem with the lecture session, I guess, right? So the component balance, I guess, let's look at an example that I have here. So looks like the example that I am going to, or we are going to look at, is the first one is going to be a single acid. So if you have, or if you know that the concentration of your particular solution is such that after adding acetic acid it's going to be at 10 power minus 3 molar, right, acetic acid, let's say, right? I want to know what are the equilibrium concentrations of the various species, right. So again, so this is a simple example we are going to start with, right. Now assume a case or look at a case where you added acid or acetic acid, in this particular case CH3COOH, which we are for which we are using the nomenclature HAC, right. So you added HAC such that the concentration of the acid in that particular system is 10 power minus 3 molar. So let's say we are going to start with the baby steps. So first I want to be able to calculate the pH for the single acid base system, and then I will also want to calculate the relative concentrations, not relative, pardon me, the relevant concentrations of the various species as in those compounds that would be in equilibrium in that particular solution. So let us go ahead and first identify the species though. So what are the species that I have, let us see, right, and in this case we are assuming that there is only HAC and then that is added to water, right. So as we know from our background, right, any acid, right, you have an acid that is put into solution, it can stay as its protonated form or the deprotonated form. So in this case what do we have? We have acetic acid CH3COOH or HAC, and it can deprotonate it and form acetate ion or AC minus. So that is what we have here. So we have H plus and AC minus. So obviously the species, what can they be? They can be the protonated form of the acid, the deprotonated form of the acid, and you will always have H plus, and obviously if you have H plus you will have OH minus, right. So these are the species or the compounds that you would expect to have at your equilibrium, right. And so then what next now? We need to identify the components. And so again a brief refresher, what are these components? They are the building blocks, right. So think of your games that you played in your childhood, if any, I guess, right. So you have these building blocks, let us say blue colored blocks, red colored blocks, yellow colored, and you can choose from individual blocks or colored individually, differently colored blocks, and form different shapes, right. But if I look at the total number of blocks of the blue, red and yellow, they are still going to stay the same, right. So these blocks or components are conservative, right. So that is the concept we are going to use to be able to solve any and all equilibrium based questions. So again components, how do you choose components? I guess you are going to choose the H plus in general always. If you want to, you can choose other components too, but choosing other components might require additional calculations. So a good thumb rule is always to use the proton or H plus and then to choose the most deprotonated form of the acid, and in that case this is going to be AC minus, right. So also I guess a care that needs to be taken with respect to choosing components is that you need to choose the minimum possible number, right, and also keep in mind that you can't choose components which you can use to form a third component itself. For example, component 1 and 2 cannot be used to form 3, they need to be independent of each other, right. So that is obviously the case here. So once I am done with that components, I guess we need to write the formation equations. The formation equations, as in I want to form my species, which I am going to list here from my components, and in general always component means there is always H2O, it goes without hand or without saying that water is always a component, right. And again we do not list it as a species because water concentration in the dilute systems we assume that it does not change, right. So that is the reason why we do not list water as a species, and water is always considered a component though, right. So here we are trying to form the species here from the various components. So let us see how we can form that, and here we have H plus one component and AC minus required to form HAC. Keep in mind that these are not chemical reactions, these are literally H plus AC minus going to HAC or equal to HAC, and you only need one AC minus to form one AC minus, one H plus to form one H plus, and H2O minus H plus to be able to form your OH minus. So once you are an expert, let us say, or not even an expert, once you are comfortable with your component balance equations and such, you can, I guess, if you want to, skip the formation reactions or equations, pardon me, not the reactions, formation equations, and directly move on to the tableau. So, what is the tableau about? This is where the crux of the matter lies. Tableau, right? We have the components listed here, H plus and AC minus, and this here is the tableau, and here we are going to have our species, and what are they? They are HAC, AC minus, H plus and OH minus, right? And now from your formation equations, you are going to populate the relevant constants here. So, how many H plus do you require to form HAC? As you see, it is 1. So, that is 1, and how many AC minus do you require to form HAC? That is 1 again. So, 1, or let us be done with H plus first. How many H plus do you need to form AC minus? None. How many H plus to form 1 H plus? 1, and in this case minus 1, and so again same case with the estate AC minus 1, 0 and 0. And obviously the last equation or the aspect that we need to look at is what is the source of all these components, right? What is it now? Keep in mind that the initial question was from we added acetic acid. So, we know that the only source of these components is from the initial acetic acid that you added. So, that is the recipe species. So, that is going to be we added HAC. So, HAC naught, again same case here, we need 1 H to form HAC and again 1 AC minus to form HAC. So, now we are done with the tableau, and now we are going to move on to the balance equations, right. So, first we obviously are looking at component balance equations. So, it makes sense to be able to write these component balances now. So, how many component balance equations will you have? So, they will be equal to the number of components that you define. So, in this case we define 2 components, they are H plus and AC minus, and so you are going to have 2 component balance equations, right. So, let us look at what they are. So, I believe H total, right, is equal to something else, and AC total, these are the component balance equations. So, if I am not wrong, they are going to be equal to the concentrations of, to be able to assist us further, I am going to again rewrite the tableau here. And this is the recipe species, the source of everything. So, this is my component balance now for H total, that is equal to 1 times HAC concentration. And what is this HAC? This is the equilibrium concentration now, right. So, H and AC minus, there is nothing in AC minus, plus H plus minus OH minus and estate or AC total, and that is here, and what is that equal to? That is equal to HAC and AC minus. So, what do we understand from this particular component balance now, right? If you look at the first equation or H total, we see that H is only present or can transform between HAC, H plus and OH minus, right. It can transform within these 3 species, and the estate can transform between HAC and AC minus, but the total estate is always going to be the constant or be a constant. And again, as we discussed earlier, what is the source of these components now? Keep in mind that we added acetate initially, right, acetic acid, and that is what we have here, HAC naught, and that is the source, and here we have 1. So, it is 1 times HAC naught, and this is your known value obviously, and here too it is going to be equal to 1 times HAC naught. So, here now how many equations do we have? We have 2 equations, but how many unknowns do we have? We have 4 unknowns, HAC, AC minus, H plus and OH minus, and what are these? These are the concentrations at equilibrium. So, we are still missing 2 further equations. Anyway, let us label this please. This is the component balance equations, right. This is what we have. So, we are done with that, and the next aspect is going to be the equilibrium equations. Again, we are trying to solve for a system that is at equilibrium. So, obviously, you are going to have equilibrium equations to assist you in your solution, right. So, let us look at what they are, and we know that we have 2 particular dissociations here with respect to acid and base. They are HAC going to H plus and AC minus, and H2O dissociating into what is it, H plus and OH minus. And we have the relevant acid dissociation constants Ka1, that is equal to concentration of H plus into concentration of AC minus by concentration of what now, HAC. And here we have acid dissociation constant for water, and that is going to be concentration of H plus into concentration of OH minus, and obviously activity of water is going to be equal to 1, thus we do not list it here. So here now we have two other independent equations, and so in total we have 1, 2, 3 and 4 equations, right. So we have 4 equations or independent equations and 4 variables, and thus we can solve for your solution now. But before we go further, I guess the point of this class is not for you to only be able to crunch up the numbers and blow someone's mind now, right. So you also want to be able to develop the intuition with respect to what it is you would expect in nature or what you would expect to see, as in that what we are plugging in here, you are adding 10 power minus 3, or you want to estimate the concentration of 10 power minus 3 molar acetic acid, right. You can always plug this in, or now we are also going to start looking at the VMINTEQ software that I requested that people install, right. The VMINTEQ software, we are going to look at that too, but you should also be able to guess your particular value, the pH at least, right. So we are going to do that. Let us see how we can solve this particular aspect, I guess, right. So what is that here? And here we are going to first solve for H plus, that makes everything easier. So we have HAC naught, right, and that we know is equal to 10 power minus 3 molar. So I am going to use that, that is going to be equal to HAC plus H plus minus OH minus, right. And so obviously now what else can I list this as though? So here we have 4 independent equations, but if you remember we already solved for ionization fractions, right. Ionization fractions, what do they give you an idea about? They give you an idea about, well, let us say the fraction of your particular protonated or deprotonated form in relation to or with respect to the total acid. So here let us try to use them. So what do we have here? We have 10 power minus 3 is equal to alpha naught into the total, what is that, I guess? That will be acetate total in this case, we will see why, plus H plus acetate total, not the concentration obviously, minus Kw by H plus. So let us see where we got this particular term from. So this is from here, so OH minus concentration is equal to Kw by H plus, and let us see how we end up with it here. We know that alpha naught is equal to concentration of HAC by concentration of HAC plus concentration of AC minus, and what is that equal to? Concentration of HAC by, and look at this term, sounds or seems familiar, and that is nothing but equation number 2, here, and so that is acetate total, right. And again you know that acetate total equal to HAC naught, so that is going to be equal to HAC by 10 power minus 3, right. Again HAC is equal to alpha naught into acetate total, or that is equal to alpha naught here into acetate total is 10 power minus 3. So we can plug that in here, 10 power minus 3 is equal to alpha naught into 10 power minus 3, which is acetate total, plus H plus minus Kw by H plus. And so I guess here now you are going to have a quadratic equation, and you can end up solving for this particular equation, right. So once you have H plus, let us move on. Once you have or you solve for H plus from that particular equation, you can immediately solve for OH minus, right. And once you have that, we know that acetate total, or you can solve for the relevant 2 equations from Ka1, let us say, right, and equation 2 and equation 3. So before we go further, we are also going to look at VMINTEQ briefly today, right. Let us see what it is about, but before we go further, Let us see if we can estimate, let us say the pH, I guess. Let me dig up the solution, but in the meantime let us see if we can also estimate the pH of the solution or concentration of H plus. So, this is to develop our intuition. Let us see how good or bad we are. So, we know that the concentration of the acid is 10 power minus 3 molar, the total anyway, the total is 10 power 3 minus 3 molar, and the other crucial piece of information is 4.7 is the pKa or the relevant pKa or the acid dissociation constant, right. So, we have these two aspects, yes. So, let us see what we can estimate here. So, one case is that I estimate that all the acid that I put in is going to dissociate, or as in HAC is going to completely dissociate into H plus and AC minus, right, but that is not going to the case. So, let us see what the pH will be at that particular case. So, the pH will be, so if you have complete dissociation, H plus is let us say 10 power minus 3, approximately equal to 10 power minus 3, and then the pH will be equal to minus log activity or concentration of H plus in this case, so equal to, the pH will end up being 3, right. So, think of this though, do you think by adding acetic acid which has a pKa around 4.7, do you think the pH can be brought down to 3? Not really. And why is that? As you know, you looked at the speciation diagram, and what do you see? 4.7, and you need a humongous amount of acid to be able to bring that down to 3. Why is that? pH 3, and why is that? Because most of it stays as HAC and it does not dissociate into H plus and AC minus. But our assumption when getting at pH 3 value, what was that I guess? We were assuming that all the acid or all the acetic acid dissociated into H plus and AC minus, and then we calculate the pH accordingly, right. But that is not the case here though. Why is that? Because pK is 4.7. So, certainly the pKa will not be or pH will not be as low. So, at best it is going to be near your pKa, but because we added considerable quantities which is 10 power minus 3 or considerable concentration pKa. So, let us go ahead and assume that the pH is going to be relatively near pH 4, right. It is going to be below 4.7, right, somewhere over here, but it is not going to be as far off as pH 3. So, this is particularly one solution I guess, right. So, let us see how we can use VMINTEQ, which is a tool or a software that will help you predict the concentrations of most scenarios, especially with respect to acid and base, complexes and precipitation and dissolution at equilibrium, right. So, I believe you were requested to source this software. Again I repeat, it is VMINTEQ or VMINTEQ, that is available for free to download, I think 10 or 20 MB, and I guess let us look at that particular interface now. Okay, so here I guess, so I am not sure if you downloaded different versions, but this is the version that I have here, right. So, I believe what do we have here? Let us look at this software for now. So, I have file, you can open input file and such if you want to, and parameters where I can specify some of the parameters such as alkalinity, which we will discuss later. PE and EH, they are relevant to your redox reactions, which we are not going to go into greater detail now, but at the fag end of the class. And if you are talking about precipitation and dissolution, for example, a solid precipitating, you have dissolved compounds, once the threshold is increased, let us say, right, you are going to have precipitation, or the inverse, let us say, if it is now dilute, let us say, you are going to have the solid dissolving into the aqueous form, right. So, that is what you are going to have here, and so this particular phase relevant to that. So, you can always have surface complexation or adsorption SCAM models, SCAM. We are going to discuss that later on at the end of the class. So, that is surface complexation reactions I believe, and gases, your particular system can be in equilibrium with gases, right, phase equilibrium. So, that is what we discussed earlier. So, this particular aspect is with respect to phase equilibrium. Again redox, as in you are going to specify your redox couple. So, you will have the oxidized form and the reduced form, and you can specify here what your couples are going to be. Similar to your conjugate acid and base, you are going to call the relevant what do we say, oxidized and reduced forms the couple. So, that is what we have here. Again we will discuss those at the fag end of the class. So, multi-sweep problem, let us say, and what is happening here, please cancel and back. Anyway, multi-sweep problem. So, here if you want to look at sweep or titration, let us say, let us say you want to see how a system changes with pH, let us say, right, or some such variables now. So, let us select that here, let us say. Yes. So you can see, right, or you can define the system in such a way that you have a particular solution and I add the titrant or change the pH, how is my system going to change? So that is what you can see here with respect to your titration. And sweep 2, I guess, with greater functionality, you can vary either pH, EH, PE or so on, or any other concentration. So with the change in, so think of this now, let us say you have your wastewater, and let us say as you change a particular concentration of your compound, any compound, let us say ligand, you want to see how the system changes, so you can use the sweep here. So anyway, we will discuss this in great detail later on. So for now I am going to move back and we are going to try to approximate the value of our particular solution or simple what do we say solution that we just looked at. So first I am going to look at various aspects. So here is one aspect, and its pH is it fixed or calculated from mass balance. So right now we do not know the pH, do we? So I am not obviously going to fix it. So I am going to say calculated from mass balance, right, and ionic strength, it can be fixed at a particular value or you can say it is going to be calculated. So I am going to leave it at calculated, but for our system ionic strength is not going to play a huge role because it is a dilute system anyway, right. So let us look at what else. So here we have look at the various units, they are molal, millimolal, micromolal, milligram per liter, microgram per liter, log molal and so on. Again, as we discussed earlier with respect to activities, right, the concentration units are molal units, and that is what you see here, they are molal units, but obviously you can use molar units, but the error is going to be around 3% because the density of water is not exactly 1 kg per liter, I guess, right. So the temperature is its standard temperature, which is 25 degrees centigrade. So let us move on, I guess. So pH calculated from mass balance, ionic strength is to be calculated, and now I need to choose my components. So add components. So for this I need to be able to look at the tableau. So let me look at my tableau. Where is my tableau here, right, and here is my tableau in a shabby manner. So let me have that in the next slide, I guess. So I have my tableau H plus, AC minus, right, and we had the relevant tableau here. So my two components were going to be H plus, let me choose H plus, I drag down and I go to H plus, and the concentration of H plus or the total concentration, H total, what is that equal to, I guess. So we know that H total, as we looked at, H total is equal to H AC naught, right, and that was equal to 10 power minus 3 molar, right. So 0.001 molar, right. Same case with estate total or AC total is equal to HAC naught, that is again equal to 10 power minus 3 molar, and that is equal to 0.001 molar, I guess, right. And let us see, let us plug this in. So obviously to be able to use your VMINTEQ, you should at least be able to calculate your total component concentrations, as in at least be able to identify the components and then be able to give the tableau or form the tableau yourself and then come up with the relevant component balance, right. So let us look at what we have here. So we are trying to edit that list, right. We will add the so this is going to be key 0.001, and I am going to add that to the list. We are going to check that later. And so because acetic acid or acetate is a organic compound, I need to choose that, show organic compounds, and then AC minus is the shortcut, or acetate, okay, here is acetate here, and again same concentration, right. Acetate total is also again 0.001 molar, and I am going to add that to the list, and as a check I am going to go and view edit list, and here I see H total is 0.001 molar and acetate total is again 0.001 molar, and I am done with that for now. I will go back to the main menu, right, and let us see where we are now, and now I will run VMINTEQ, right, and let us look at what we have. So let us look at this now. The pH is 3.9. So the first aspect to look at is that we approximated the pH earlier, right, and that we said was going to be around 4, right. So let us check our value with what we have here, and you see that the pH that they calculated not they, pardon me, the model calculates is 3.9. So we were relatively or remarkably closer, or we were able to predict remarkably we did a good job in predicting the pH value, right. So you should try to develop that particular intuition as you go along. And ionic strength, as you see here, it's relatively low. Yes, that's something that you would expect. And here now, in this particular section, you see the concentrations of various species. So what were the 4 species that we listed in our particular solution? They were acetate ion and acetic acid, H plus and OH minus, and that's what you see here. And obviously the system also gives you the activity, and because the ionic strength is low, you more or less see that the concentration and activity of the relevant compounds are more or less the same. But if the ionic strength is high, the activity is going to then be low, right. So this is something that you need to understand. So let me also look at view species distribution. So this is the tab here, view species distribution. What does that give me an idea about? So I want to look at in which form is acetate going to be in. So it tells me that only 12% of the total acetate is going to be as AC minus and 87% of the acetate is going to be in the form of HAC, right. So this is what we understand too, right. And let us look at what we have there, I guess. Back to main output menu, and if I switch, so what do we see here? This is our system, HAC, and this is AC minus, pKa is 4.7, right, and what was our current pH value? I think something around 3.9, so 3.9. So what do you see here? You see that most of it is present as HAC and little or some of it, only some of it is present as AC minus. So let us check our values here and display saturation indices. So that is why it shows only 12% is present as the deprotonated form or acetate, and 87% is present as the acid, right. So that is what we would expect, and that is what we just observed too, right. Come back to here and you can look at equilibrated mass distribution, but not of great use in acid based systems because everything is going to be in the dissolved form, right. So take home message here is that you can get the concentration, you can get the pH, right, and you can also get the species distribution, not species I guess, speciation, and also the relevant concentrations of all your species. So today we were able to solve a simple example with respect to adding an acid, a known quantity of acid to water, and then calculate what is the pH and the equilibrium concentration of all the various species there, right. And then we also looked at how to use visual MINTEQ, and we are going to use visual MINTEQ throughout the class, right, because that is going to help you, right. You want to conduct an experiment, yes sure, if you have a lot of time, resources, and you have, and I am sure you do not have a lot of time to spare. So obviously visual MINTEQ is going to help you cut down on the calculations and your laboratory time, right. So in the next class again we are going to go through our next lecture session again. We are going to go through with our more complex or slightly more complex examples, and for this session I am done. Thank you.